So let's take a look at our first squeeze theorem example, example 1. So in this example, everything's given to us. So this is one of the easier type of squeeze theorem problems you could see, where they actually give you this inequality, this compound inequality. The function we're trying to find the limit of, some lower function and some upper function. So these are sort of the bounds, the lower bound and the upper bound. And they're telling us the limit near x equals 2. So what is the limit of f of x as x goes to 2? So we can go ahead by taking this compound inequality and just acting on it with the limit as x goes to 2. So I'll have negative the limit as x goes to 2 of x, right? And truly this is actually the limit of negative x, but I'm just choosing to factor out this negative 1, which we know we can do for limit laws. So go ahead and do that. Less than or equal to the limit as x goes to 2 of f, less than or equal to the limit as x goes to 2 of x cubed minus 4x squared plus 3x. So now each of these lower and upper functions, they are polynomials. That means they're continuous. That means we can take the limit of them by direct substitution. So we can just plug in 2 into each of these expressions. So the lower portion becomes the limit of x is 2, and then times negative 1, so we have negative 2. We don't know what x is, or sorry, excuse me, we don't know what f is, so we can't actually explicitly, directly calculate that, so we'll just have to copy paste for now. And then here, if we go through all the arithmetic here, we will find that this also actually gives us negative 2 when we plug in 2. Well, there's only one real number that is simultaneously greater than or equal to negative 2 and less than or equal to negative 2, namely negative 2. So by the squeeze theorem, so I'm going to say the squeeze theorem, you can read this arrow symbol here, you can read this as implies. So this means the squeeze theorem implies that the limit as x goes to 2 of f must be equal to negative 2.